times a plus b times xi plus 1. Now I have 3 equations and 2 unknowns. It's overdetermined. So now this is of the form a matrix times the coefficient vector. Let's call it the coefficient vector c equals values f and f vector. And again, you solve that with this least squares step. Least squares. And the recipe is you solve the system m transpose times m times unknown vector c equals m transpose times f vector. And then you are dealing with the 2 by 2 problem, and from that you get the unknown coefficients a and b. Once you have that, well, then you have the derivative here, right? The derivative of the line is the same. It's constant everywhere. So you have fi prime is, well, L prime, and that is just b. Using this. Which approach is better? Fitting a parabola through the 3 points exactly versus computing this approximating line. Which one is better? Which one is better? If all your samples originated from a line, if this was your scattered data set, okay, all your samples came from a line, then you would like to reproduce that line perfectly, right? In an ideal world. And you can ask the question, okay, if all my measurements, my sticks, my data came from a line or were lying on a line to begin with, which of these schemes would give me the slope of that line? Would it be this scheme or that scheme, or both schemes? Okay, that's one way. The other thing is, okay, if all my sites were to lie on a parabola to begin with, if all my scattered data were samples that indeed lie on a parabola, then it would be super if my gradient estimator computed estimates that are indeed the perfect, the correct, the exact derivatives of a parabola. Which scheme can produce the perfect gradient for a parabola if all my sites and my function values there relate to a parabola? This scheme or that scheme, or both schemes? So this all relates to the issue of polynomial precision and so forth. Which scheme is the better one, or what type of a scheme does one need? If one wants to reproduce a certain class of functions or polynomials, linear, quadratic, cubic, then one has to build this apparatus in such a way that if my data come from such a class of a polynomial, I reproduce it exactly. It's a big topic in its own right. And now we have to talk briefly about the 2D setting, the triangle case. How do we get the derivatives in the 2D setting, where it's no longer just the derivative, but we get 2 derivatives, when x and y, right? We get a gradient vector. So that is the next step. Next time we can use it. How do we get the derivative in the scattered data setting when the sites live in the plane, xy plane? So bivariate setting. Bivariate setting. Gradient estimation. Gradient grad estimation. Okay, what do we have in this case? Case number 1 is related to fitting a smooth paraboloid through the data. And case number 2 is related to finding a best possible plane, approximating the sticks. So the analogs of those cases over there were computing a least squares. It has to become a least squares now. A least squares approximating say quadratic. What does this look like? So my data consists of sides in the xy plane with associated function values. So I have a side, another side, another side, and another side. I want to have enough sides. 2, 4, 6. 6 is a good number. But I want to make it more ugly. I make it 7 points, okay? So and now I have my sticks here. These are the dependent variables, dependent values. And so in order to approximate a gradient here, right, what is a tangent plane? That's the way to think about it, right? An osculating plane, a tangent plane. I need to construct somehow an approximating quadratic function, a smooth fit. Huh? And then I will differentiate this smooth polynomial at this particular location here to get the estimate of the tangent plane or the gradient at this location there. Now again, the setting is more general because, well, I have a local neighborhood. In the 1D case, the local neighborhood is always left, center, right. Huh? Left, center, right. In the arbitrary scattered data setting in the plane, well, I don't have that, but I have a triangulation. We assume that we have triangulations, right? So there is a triangulation here. These sides would be at least triangulated. That's what we said, right? There's a triangulation here. Triangulation-based methods. So these are the function values here. Sticks. And so if there is a triangulation that has this guy at its center, then this set of triangles is called the platelet. Huh? All the triangles going around the center vertex, these triangles define the so-called platelet of that vertex. All these triangles share this vertex as a common one or as a shared one. That's the platelet, and it's always a good idea to consider this set of local triangles to approximate something. Huh? Because there was a reason you want to assume to use this triangulation in the first place. Huh? So the triangulation should reflect somehow a good way to define a neighborhood. Huh? If that's not the case, then it's a bad triangulation. So again, these triangles define the platelet around that center vertex. And now I want to write down this particular quadratic polynomial. So the quadratic fit, is it a fit? No, it's not really. Quadratic. The quadratic will be of the following form. It's a quadratic polynomial depending on two variables, x and y. And it will be c2, 0. No, I should write it differently. I should say it's c00 plus c1, 0x plus c0, 1y plus c1, 1xy plus c2, 0x squared. I think you see how the powers go and the indices go. Plus c0, 2y squared. Okay. So I have 6 coefficients for this quadratic polynomial. And the monomials I have here is the constant x, y, the mixed x, y, and then the x squared and the y squared terms. So now I need to write down the local constraints that I would, for this quadratic to interpolate or to approximate. In this situation, how many constraints do I have? How many function values do I consider to construct this guy? How many? 1, 2, 3, 4, 5, 6, 7. I have 7 data to be used to construct this guy, which only has 6 degrees of freedom. That's why I only can construct this in an approximating sense, right? Because I have a small number of degrees of freedom, then I have constraints, things I would interpolate. So therefore, I have the least squares set up, least squares problem set up. And now you assume that you index these things locally, right? Say this is locally function value 1, this is function value 2, function value 3, function value 4, function value 5, function value 6, and function value 7, okay? And this number, how many local data you have, this changes, of course, throughout the triangulation, because the valence, right, of these vertices is different all over the place. So, well, again, you assume that you have an overdetermined system. So the coefficient vector is now coefficient vector C0, 0, C1, 0, C0, 1, C1, 1, C2, 0, and C0, 2. And you want to interpolate, in this specific case, those values from F1 up to, well, in general, there will be Fk, right? There will be k vertices in this local neighborhood. Here, k is 7 in this particular platelet situation. And I have, well, 7 or k equations. So the first one is 1, then it is x1, y1, then I have the mixed term x1, y1, then I have x1 squared, then I have the term y1 squared. Okay? The last equation will be 1 xk, yk, mixed term xk, yk, then I have xk squared, and the last one is yk squared. Okay, so these are the k lines, and here are the breaks. Okay, I just indicate the breaks. Okay. So these will be your k equations. Again, this is some kind of matrix times some kind of coefficient vector equals some kind of function values, and you use the same trick. You solve the normal equations by using m transpose times m times c equals m transpose times f. And then you have a 6 by 6 problem to solve for the 6 coefficients. And then you get, when you solve it, you get your coefficient vector, your C0, 0, up to the last coefficient is C0, 2. Okay. Why did we construct this? Oh, we just want the tangent plane. We just want the gradient. So that means we have to now take this particular polynomial, and we have to differentiate it with respect to x and with respect to y, and evaluate it at the location where we need that plane, right? So now we do that next. And then we have the estimate. So we needed is the gradient of that guy. Needed is the gradient, grad q, which is grad q, which is a vector quantity consisting of 2 components. The first one is, what is it? When I differentiate that with respect, I get C1, 0 plus, what's the other one? C11 y plus, what is it? 2 C2, 0x, right? All right. That's the first component. The second component is C0, 1 plus mixed term C11 times x plus 2 C0, 2 times y. So that's the gradient. And we don't need it everywhere. We need to evaluate this guy at the center point, right? And then we evaluate that. Evaluate grad q at the center side, right? Center side. Whereas the center side is the guy in the middle here, for which we need the gradient estimate, center side. Okay. So now I can also do this very quickly for the bivariate setting. It's not much more difficult than the line. Now we just find the best possible plane that approximates a bunch of sticks coming out of the floor, right? So the least squares linear approximation, that goes very quickly. What is our setting? Our setting is xy plane. and f values. We have a bunch of values here, and in the middle, oops, values here, values here. And we want to construct the best possible plane, right, for this. So we want to get some kind of best possible plane. That might look like this. But it doesn't pass through any of these sticks, right? It just gets very close to them. So this is, again, my function value 1. This is function value 2, function value 3, function value k minus 1, and this would be function value k. Right? Again, we assume that there is this underlying triangulation there that we have. Right? The platelet, and we have in this case 5 points for a plane equation, linear equation takes on the form f, well, linear plane, I should call it L, right? L for linear. So I have a linear equation x and y, and it's nothing but a constant plus bx plus cy. And the apparatus works just as in the case before. I set up my conditions, my constraints, so I have all my sides. I have only 3 unknowns, a, b, and c. And I want to approximate the values f1 up to fk in the local neighborhood, local numbering. And then I plug the different sides in there with their xi, yi coordinates. So I have 1, x1, y1, and so forth. And the last one is xk, yk. And again, I would have a k row system. So this is my system. M times vector c equals vector f. You solve m transpose times m times c equals m transpose f. And you get your coefficients a, b, and c. And what do you need? You only need the gradient of the plane. But the gradient of the plane is constant, because when you differentiate with respect to x, you get b. When you differentiate with respect to y, you get c. Should be, because it's a plane, right? It has the same normal or the same gradient everywhere. So therefore, you get this plane here that I have constructed globally. You associate that plane's or that linear polynomial's gradient behavior, derivative behavior, here. And you have the gradient of L is constant everywhere, namely b and c. And that's what you use as the gradient x, b, and gradient y, c for this side. This might be cheaper. Is it cheaper to compute than the quadratic? Yes, it is, because this is ultimately a 3x3 system. The quadratic was a 6x6 system, right? But you always can store the inverted form of a 3x3 matrix or 6x6 matrix in symbolic form and can use it. You don't have to compute it inverted all the time. Again, you can symbolically solve these problems already beforehand. Okay. Now, last thing I talk about is why do we do this, or what do we have at this point? And that's where I will continue next time. The use has to be of some use, right? So the use is this. We have our triangle in the plane. This is our building block. All we have to understand is the building block. We have 3 sides locally, and besides the sticks or the function values at these sides, by this point we also have computed little tangent planes, right, at all these corners. Huh? So we also know derivative behavior, right, because we have computed the tangent plane here, we have computed the tangent plane here, and we have computed the tangent plane there, right? Okay. Now we have to follow our intuition. What type of a patch is this when we specify or when we are given as input
a stick, and a stick, and two derivatives, namely this derivative and this derivative, this one and this one and this. So how many parameters is that? 3 values plus 3 gradients, but each gradient is 2 components, so it's 9, right? 9 pieces of input. So this will be called the 9-parameter cubic. Okay, the input is 3 f values plus 3 gradients at the corners, plus 3 gradients. Estimates, really, gradient estimates at the corners CI. Right, those are our CI corners, C1, C2, C3. Okay. What kind of curves are these? Point, derivative, derivative. What is that? Along the boundaries, we have the curve case, right? The one-dimensional case. So the curve case is this. I have a side, I have a side, I have a stick, I have a stick, I have a derivative, I have a derivative, right? This is the case I have at each boundary. So what kind of a degree do I need to interpolate to these 4 pieces of information? Value, value, derivative, derivative. Cubic. Huh? Cubic. I need a cubic to do that. Okay. I will continue next time so that you already have an idea. You need cubic boundary curves. Huh? So they will have Bezier polygons like this. Huh? Okay. So 4 control points for each boundary curve. So in looking at this abstractly, then here's my triangle, right, in the domain. At the corners, I have function values. And then these interior Bezier points, 2 interior ones per edge, are also implied by the gradients, right? So this guy is implied, this is implied, this one is implied, that one is implied, this one is implied, this one is implied. There's something missing. There's something missing there in the middle. Because a Bezier patch of this order, of this nature, requires also a Bezier point to live there, to have this structure ultimately. So I need this guy in the middle, which is, what is it? Is it implied or is it specified by something? No, it's not specified, because the sticks and the tangent planes of the gradients only imply the information around the 3 corners, but not the stuff in the middle. I leave you with that. Think about how to pick the stuff in the middle. You can pull or push this down. What is a good choice for that guy? All right. Bye-bye. Also, Livermore, bye-bye.